All right, welcome to your first pre-lecture. So we're going to talk today really fast, and we're going to review engineering calculations. Now I know you've had a full year of engineering classes, but there are a couple things that I want to review really quickly to make sure that you've got a really good foundation for this course. So you may have seen these concepts in other courses, but we're just going to take some brief time to review. At any point during any of our pre-lectures for this semester, feel free to pause at any point. These lectures are designed to be paused so that you have the time to write in your notes, and make sure that you're using the templates on Canvas. They have these exact same slides but with some blanks so that you don't have to take a lot of notes and you can really kind of sit and absorb the information. So let's get started. So first things first, we're going to talk about units and dimensions, and I'm sure you've done this in other courses, but let's make sure that everybody's on the same page going forward. So whenever we have some kind of a measured or counted quantity, it's going to have two things associated with it. It's going to have a numerical value, which is something like 3.56, and it's going to have a unit, whatever that 3.56 is of, whatever we're measuring. So in this class, whenever you have a number on the page and you're circling a final answer, we're also going to be looking for units. That's going to be really critical in this class because we're going to have lots of different quantities that we're going to learn about, and the units of those quantities are different. So remember that you're always going to have a numerical value and you're always going to have a unit. Now, we sometimes hear the word dimension come up, and that simply means that it's a property that can be measured or calculated by multiplying or dividing other dimensions. So for the purposes of this class, some common things that you'll see measured are things like length, time, mass, and temperature. So these are things that we have analytical tools for that we can measure. But then we'll also see quantities that are calculated. So calculated quantities or dimensions are things like velocity, which is length divided by time. We can also have volume, which is length cubed, or we can have density, which is mass divided by volume. But if we really want to get down to simplistic terms, it's mass divided by length cubed. So in this class, we'll see dimensions that are both measured and calculated as we go forward. Units are like algebraic variables. We can add, subtract, multiply, or divide those variables, but they act like a variable when we're doing so. And that's going to be really important because there are specific rules about adding and subtracting that are different from multiplying and dividing. So it's important that two quantities can only be added or subtracted if the units are the same. Okay, so take a second and think about what that means. That means, for example, if I have 3 centimeters, I can subtract 1 centimeter and get 2 centimeters if I want to because they have the same units. But if I have 3 meters and I want to subtract 1 centimeter, those are not in the same unit, so one of them has to be converted first. And the reason that we say that this is like algebra is because if you take the unit and you substitute it for something like x, we can subtract an x from a 3x and get a 2x, but we can't subtract a y from a 3x and get a 2x. It doesn't work that way. So be very, very careful when you're adding and subtracting units that you're in the same, if you're adding or subtracting quantities that you're in the same units. This is a really great way to check yourself as you're going through the problems this semester, is to look at your units and make sure you're following the right rules for units. If we have numerical values and we are multiplying or dividing, so now we're in a different place, multiplying and dividing, we can always combine those units by multiplication or division. So as an example, we can take 3 newtons, multiply it by 4 meters, and get 12 newton meters. That is a unit that's how you've probably seen in physics before, is force times a length, right? And we get a new unit out of that. We can also do things like division, where we divide 5 kilometers by 2 hours and get 2.5 kilometers per hour. Those are units that make sense, but on occasion you're going to multiply and divide and you're going to get units that don't always make sense. So sometimes that's not a bad thing, but it will help tell you a little bit about whether or not you're actually adding or, multiplying or dividing quantities that make sense going forward. So this is a great way to check yourself. Remember, you can only add or subtract units if they have the same units, but if you multiply or divide, you get compound units. You can also talk about conversion of units. So you've probably done conversions of units many, many times, but it's worth reviewing. We have conversion factors whenever we convert units, and those are ratios. That is one unit in terms of the other. So we have things like x of unit whatever, and y has a different unit, and you can divide the two. And those are it's basically the proportion between how much of x is equal to how much of y. So we always convert from one unit to another using one or more conversion factors, and that's through multiplication. So a very common one that we will see as environmental engineers is going between different forms of grams. So in this example here on this particular slide, let's try and convert milligrams to grams. Well, we know that 1 gram is equal to 1,000 milligrams, and that is the conversion factor. That ratio right in the middle is your conversion factor. Let me grab my laser pointer. See, right there, that's your conversion factor. And then let's say, for example, that we had 36 milligrams of something, but it made more sense to do the calculation in grams. Well, we would take the 36 milligrams, we would multiply it by the conversion factor, and then we would get the 0.036 grams. So I'm sure you've done unit conversions before, but if you haven't, this is very common to do, especially in the environmental engineering field, especially when we have small quantities that need to be represented in different units. So if it's new or confusing, take a pause and make sure you understand it. Always feel free to ask questions in class as we go through. It's going to be important for you to carry your units along with your calculations to avoid making mistakes. So it's one of the most common things that I tend to see with students who are working on problems in a mass and energy balance course is that their units are not correct. So if you bring your units along with you and make sure that you have your units as you go through your calculations, it's going to help you avoid some errors. So let's do an example really quick. We're going to use what we call a dimensional equation to give you an example of what the unit conversion would look like. So a dimensional equation is a series of conversion factors used to convert from one set of units to another. So basically, it's what we did in that example on the past slide, but many, many times in a row so that we get to the final unit that we care about. So a dimensional equation is going to have a general form. We're going to take a quantity in a specific set of units, and we're going to multiply it by one conversion factor, and then maybe we need another one, and then maybe we need another one, and as many as we need, that's going to be the dimensional equation, starting with the initial quantity and then multiplying it by a series of conversion factors. So let's do an example. Let's convert acceleration from 1 centimeter per second squared to 1 kilometer per year squared. Now, a great thing to do right now is to pause the video and try this yourself. I will put the solution up on the screen in just a moment, but I do recommend as we go through the semester that you take the time to pause the video and make sure you understand how to do it yourself, because I won't be there to help you on your exams. So take a pause right now. All right, hopefully you took that pause. Let's pop the solution up on the screen. See if you got it. So when we convert from centimeters per second squared to kilometers per year squared, we need to first convert centimeters to kilometers, and then we need to think about seconds to years. So there's two things going on here. And one of the key components of this example is that squared associated with the time. So anytime we're converting with time, we're going to have to square quantities, and that's really critical. So you'll see here that this example first takes the 1 centimeter per second squared and it puts it on the right to form, on the left, to form the dimensional equation. And then there's that series of conversion factors before we get to our answer. So you'll see that we know there are 3,600 seconds per hour, but because we have seconds squared, we need to square both the quantity and the unit. So we need to square the 3,600 and the 1 for the hour. We know there's 24 hours per day, but again, those quantities are squared. There's 365 days per year. 1 meter is equal to 100 centimeters, and then 1 kilometer is equal to 1,000 meters. And if we do all that math, you'll see that final answer there of 9.95 times 10 to the 9th kilometers per year squared. So hopefully you got that answer, and if not, no big deal. Take a pause, Make sure that you understand each step, and if you have questions, please come see me in office hours. All right, last thing we want to talk about very quickly are systems of units. Systems of units have the following components. They have base units. They have things like mass, time, length, temperature, and then these other quantities like electrical current and light intensity that you would learn if you take Physics 2. We also have multiple units inside a system of units, and these are multiples or fractions of those base units. So if the base unit is time, a multiple or a fraction of that is minutes, hours, seconds. Then we also have what are called derived units, and these are compound units that are derived basically by multiplying or dividing those units. So remember, when we multiply or divide, we can get new units. So those are our derived units in our unit systems. So they're equivalent of compound units. So a really good example of this that you hopefully saw in Physics 1 is that 1 Newton is equal to a kilometer times a meter per second squared. So remember that force is measured in newtons, and force is equal to mass times acceleration. Mass is measured in not kilometers, that would be strange, kilograms, and our acceleration is measured in meters per second squared. So if we multiply the two of those together, we get a kilogram times a meter per second squared, and that's what we define as a unit. So a newton is a derived unit. Last thing we'll mention here is that we're going to use the SI system throughout this semester, and I want to point out what the base units are in the SI system. So again, remember, you can pause the video at any point if I'm talking too fast. In our base units in the SI system, we have length measured in meters, mass measured in kilograms, moles in a gram mole, time in a second, and temperature in a Kelvin. We won't see electrical current or light intensity in this class, but if you're curious, the base unit in the SI system, which is the same as the metric system, is an ampere for electrical current and a candela for a light intensity. We'll also see some common derived units, and the ones that we're going to care about in this class are volume, which we typically see in a liter, force, which we see as a Newton, pressure, which we see as a Pascal, energy or work, which we see as a joule, and power, which we see as a watt. And the one thing that I want to make sure that we point out on this slide is that on the very right side of this table, you have the equivalent in base units. So sometimes when you do your calculations, you won't necessarily get a liter for volume, but you might get a meter cubed. Same with the Newton, you might not get a Newton out of the calculation that you're doing. You might get a kilogram times a meter per second squared, but we know that that's a Newton. So knowing what the equivalent is in base units is a good way for you to check yourself and make sure that you understand what you got out of that specific calculation. All right, hopefully this has been a really good quick review on units. If there are any questions, please don't hesitate to reach out, and that's going to finish us up for this particular pre-lecture.